The most profound force in the cosmos comes from absolute nothingness. This is the paradox of vacuum energy, a hidden power within empty space that could have birthed our entire universe or may one day tear it apart. By the end of our journey, you will understand why this mysterious nothing is the most important something in existence. We will explore how a seething quantum void holds the keys to both creation and annihilation, revealing what keeps our reality stable and what could trigger its silent end. How do you picture the emptiness between the stars? Classical physics painted a picture of a perfect vacuum as a silent, sterile void. But that image is an illusion. The quantum realm reveals that what we call empty space is anything but empty. It is a seething, bubbling sea of spontaneous activity, a foam of energy fluctuations constantly churning at the smallest scales. This is the quantum vacuum, and its nature is governed by one of the most fundamental principles of reality, the Heisenberg uncertainty principle. This principle tells us that on tiny scales and for fleeting moments, energy can be borrowed from nowhere, allowing pairs of virtual particles to spontaneously spring into existence. A particle and its antiparticle partner can appear together, live for an unimaginably brief instant, and then annihilate each other, returning the borrowed energy to the cosmos. This endless dance of creation and destruction is not happening within space. It is what space itself is made of at its most fundamental level. This zero-point energy is a fundamental property of the fabric of the universe, meaning that even in the deepest, darkest voids between galaxies, far from any star or planet, there is a tremendous latent activity. The void is alive with transient existence. This foundational concept completely redefines what we mean by nothing. Nothing is not an absence. It is a simmering potential, a hidden ocean of energy waiting just beneath the surface of perception. And it is from this restless nothing that everything may have come. This restless quantum sea has a minimum energy level, a fundamental hum that can never be silenced. We call this zero-point energy the lowest possible energy that anything can ever have. Think of it like a guitar string. Even when it is not being played, when it is in its state of absolute rest, it still possesses a tiny, inherent vibration. It never truly becomes still. In the classical world, we imagine we could cool a system down to absolute zero, where all motion ceases, but the quantum world defies this. At the absolute coldest temperature possible, a quantum system would still be buzzing with this residual zero-point energy. It is a property of reality itself, an unending background noise woven into the fabric of space. This is not just a mathematical idea. We can observe its effects. One of the most stunning demonstrations is the Casimir Effect. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in an absolute vacuum. You would expect nothing to happen, but something remarkable occurs. The quantum fluctuations of the vacuum, those virtual particles popping in and out of existence, exert pressure. Outside the plates, any wavelength of fluctuation can exist. In the narrow gap between them, only certain wavelengths can fit. This creates a difference in pressure. With more activity pushing on the plates from the outside than from the inside, the plates are gently forced together. It is a real, measurable force caused by the sheer energy of nothingness. The void itself is pushing them. This proves that the quantum vacuum is not a passive stage. It is an active participant, a field of immense latent power whose presence we can literally feel. And if the vacuum holds this much energy, what happens when we look at it on the grandest scale of all? This latent power of the vacuum presented a puzzle on the grandest possible scale. When Albert Einstein was crafting his theory of general relativity, his equations described a universe that was dynamic, one that should either be expanding or contracting. Yet, the scientific consensus of his time held that the cosmos was eternal and static. To reconcile his brilliant math with this flawed assumption, Einstein made a small but profound adjustment. He introduced a fudge factor, a term he called the cosmological constant. This was a repulsive force, an anti-gravity woven into the fabric of space itself, which would perfectly balance the inward pull of gravity and keep the universe forever still. It was a clever fix, but it was wrong. When astronomer Edwin Hubble observed that distant galaxies were all rushing away from us, proving the universe was not static but explosively expanding, Einstein realized his error. He famously renounced the cosmological constant, calling it his greatest blunder, and it was largely abandoned by physics for decades. The story, however, does not end there. In a stunning twist of fate, the cosmological constant has been resurrected. In the late 1990s, astronomers made a discovery that shook cosmology to its core. They found that not only is the universe expanding, but this expansion is accelerating, speeding up over time. Some mysterious repulsive force, stronger than gravity on cosmic scales, is pushing everything apart. And the leading candidate for this dark energy is none other than Einstein's discarded idea. The energy of the quantum vacuum itself could be providing that push. The cosmological constant is now seen not as a mistake, but as a potential description of the vacuum's own energy, a fundamental property of empty space that drives the cosmos apart. So the greatest theoretical blunder became a cornerstone of modern cosmology, directly linking the frantic, microscopic dance of virtual particles to the ultimate fate of the entire universe. But if this vacuum energy is real and this powerful, it presents a new and far more terrifying puzzle. This connection between the quantum vacuum and cosmic acceleration is one of the most compelling ideas in modern physics. The energy density of empty space itself could be the dark energy pushing the universe apart. It is an elegant solution, a single concept explaining the largest scale behavior of the cosmos from its smallest scale nature. Yet this elegant idea comes with a staggering problem, a numerical catastrophe that threatens to unravel our entire understanding of physics. When theorists calculate how much energy the quantum vacuum should contain, based on the sum of all those fleeting particle fluctuations, the number they get is absurd. It suggests a vacuum energy density so immense that it should have torn the universe to shreds in the first instant of its existence. This theoretical value is not just a little too big. It is wrong by a factor of 1 followed by 120 zeros. This is the largest discrepancy between prediction and observation in the entire history of science. To grasp the scale of this error, imagine predicting that a single grain of sand would weigh as much as the entire observable universe. The difference between that prediction and the grain's actual weight is still infinitely smaller than the gap in our vacuum energy calculation. This is not a small oversight. It is a screaming alarm that we are missing something fundamental. Either our theories of the quantum world are profoundly incomplete, or there is a miraculous cancellation, a symmetry or mechanism we have not yet discovered that almost perfectly nullifies this vacuum energy, leaving behind only the tiny, residual effect we measure as dark energy. This gaping void in our knowledge stands as a silent monument to the fact that our greatest theories, general relativity and quantum mechanics, are still at war with each other over the true nature of nothing. This staggering error is a direct challenge to our most fundamental theories, but the vacuum holds another secret, one that is woven into the very substance of matter. To understand it, we must meet another invisible field that fills every inch of our reality, the Higgs field. While the quantum vacuum is a seething sea of temporary particles, the Higgs field is a constant, treacly presence throughout the cosmos. Its most famous role is giving other elementary particles their mass. Think of a famous person trying to walk through a crowded room. The crowd gathers around them, clinging and slowing their progress. That resistance is like mass. The Higgs field is that crowd, and by interacting with it, particles gain the property we experience as weight and inertia. For our universe to exist as it does, with atoms and chemistry and life, the Higgs field must be in a very specific state. Picture a ball resting peacefully at the very bottom of a deep valley. This low-energy state is what we call our vacuum, and it feels perfectly stable and permanent. But what if our valley is not the only one? What if it is merely a small dip on the side of a much, much deeper chasm? This is the terrifying possibility of the false vacuum. Our stable-looking vacuum might only be metastable, temporarily safe, but not in the most stable state possible. It is like a ball perched on a small ledge high up on a mountainside. It seems secure, but a sufficiently strong nudge could send it tumbling down into the true bottom, the true vacuum far below. In cosmic terms, that nudge could be a random, high-energy quantum fluctuation, a chance event in the vacuum's endless dance. If such a decay were to be triggered, perhaps by a powerful particle collision, it would be catastrophic. A bubble of true vacuum would form at that point and expand outward at the speed of light. As this bubble wall moves, it would rewrite the laws of physics in its wake. The Higgs field inside would settle into its new, lower energy state, and in doing so, it would fundamentally alter the properties of every particle it touches. Atoms would instantly cease to hold their structure. The very forces that bind matter together would dissolve. Reality as we know it would simply vanish, replaced by something entirely alien and almost certainly incapable of supporting life. The end would be instantaneous, silent, and absolute. A final whisper from the nothingness that first gave us everything. This silent apocalypse could begin with a single, random pop in the quantum foam. Somewhere in the vast emptiness between galaxies, a fluctuation in the vacuum, a little more energetic than all the others, could serve as a nucleation point. It would be the cosmic equivalent of the first ice crystal forming in supercooled water. At that precise location, the Higgs field would tunnel through its energy barrier, falling from its precarious perch on our seemingly stable ledge down into the true, absolute bottom of its potential. In that instant, a bubble of true vacuum is born. The moment it forms, the new rules are written. The fundamental constants that govern our universe, the strength of forces, the masses of particles, all of it would be instantly and irrevocably reset to new values. This bubble would not expand like a fireball of destruction. It would be a wall of pure transformation, a boundary of new physics rushing outward at the speed of light. There is no force in our universe that could stop or even slow it. You would have no warning. One moment you are living your life on Earth, and the very next Planck second, the bubble wall sweeps through our solar system. The change is not violent in the conventional sense. It is far more absolute. As the new vacuum state washes over you, the electromagnetic force that binds atoms into molecules might simply cease to exist in its current form. The very concept of an atom falls apart. Electrons would no longer orbit nuclei. The nuclear forces that hold protons and neutrons together would vanish. Every piece of matter, every star, every planet, every living thing would instantly and silently dissolve into a cloud of fundamental particles, their structures erased by a new set of physical laws that are almost certainly incompatible with complex matter or life as we know it. The end of reality would be a quiet one, a wave of nothingness that unmakes everything in its path, leaving a uniform, alien cosmos in its wake, and the most unsettling part. This process could have already started somewhere in the distant cosmos, and the wave of annihilation could be on its way to us right now, utterly undetectable until it arrives. The storm of the quantum vacuum is relentless. To grasp its raw mechanics, we must look at the very heart of this seething activity, the quantum fluctuations themselves. Think of empty space not as a still pond, but as a stormy ocean. At every single point, energy levels are in a constant state of turmoil. Waves rise and fall with incredible speed. and these temporary swells in energy are not empty. They are the birth of something from nothing. For a fleeting moment, a particle and its antiparticle, a virtual pair, can borrow this energy and spring into existence. They live for a time so short it is almost impossible to conceive. And then they collide, annihilating each other and returning the energy to the vacuum from which they came. This endless, frantic dance of creation and destruction is what fills the void. But are these virtual particles just a convenient mathematical trick? The evidence says they are profoundly real. Their ghostly presence has been measured. In the late 1940s, physicists Willis Lamb and Robert Rutherford were studying the hydrogen atom. According to the best theories of the time, two of its electron energy states should have been identical, but their experiments revealed a tiny shift, a slight difference between them. This Lamb shift was a small anomaly that could not be explained by the old physics. The answer came from the quantum vacuum. The constant appearance and disappearance of virtual electron and positron pairs around the real electron subtly alter its environment, changing its energy just enough to create that measurable shift. The nothingness was leaving a fingerprint on the atom itself. This influence extends to the most extreme environments imaginable. At the edge of a black hole, where gravity is so intense that not even light can escape, the vacuum's activity takes on a world-ending role. The immense gravitational field warps the fabric of space-time, affecting the creation of these virtual pairs. Normally, they annihilate each other instantly. But if a pair appears right at the event horizon, one particle can fall into the black hole while the other escapes into space. From our perspective, the black hole has just emitted a particle. This is Hawking radiation. Over astronomical timescales, this slow, steady trickle of particles, born from the twisted vacuum near the event horizon, causes the black hole to lose mass and eventually evaporate completely. So the same quantum activity that subtly tweaks an atom here on Earth is also responsible for the eventual death of the universe's most terrifying objects. The virtual particles of the empty void are not just a theoretical curiosity. They are active players, shaping the fate of everything from the smallest atom to the largest black hole. This restless energy of the void is not just a theoretical idea. We can reach out and feel its push. One of the most beautiful and direct proofs comes from a simple yet profound experiment, the Casimir Effect. Picture two perfectly smooth, uncharged metal plates placed parallel to each other in an absolute vacuum, with a gap between them narrower than a wavelength of light. In our everyday world, you would expect nothing to happen. They are just two inert pieces of metal in an empty space, but the quantum world has other plans. The space between those plates is too small to accommodate every possible kind of quantum fluctuation. Only certain wavelengths of virtual particles, specifically photons, can fit into that tight squeeze. Outside the plates, the vacuum is a wild party, with fluctuations of all wavelengths pushing in from all sides. Inside the gap, the guest list is severely restricted. This creates a pressure imbalance, with more activity pressing on the outer surfaces of the plates than on their inner faces. The plates are pushed together by the sheer energy of nothingness. It is a real, measurable, attractive force that appears from the vacuum itself. This is not a subtle theoretical prediction. It has been confirmed by numerous precision experiments. The void is not passive. It exerts a physical force we can measure, a gentle but insistent pressure born from the endless creation and annihilation happening all around us. This tangible force provides stunning confirmation that what we call empty space is a cauldron of latent power, a foundational energy that shapes the very fabric of our reality. Yet this same violent vacuum activity holds the key to our very existence. We must journey back to the first fleeting moments after the beginning, to a time when the vacuum was not a simmering sea but a raging fire. In this primordial state, A hypothetical field called the inflaton field is thought to have dominated the cosmos. Like the Higgs field, it permeated all of reality, but it was trapped in a state of incredibly high vacuum energy. This was a false vacuum of a different kind, one of immense creative potential rather than destructive instability. Think of a ball resting high up on a vast, flat plateau, filled with a tremendous store of pent-up energy. This unstable configuration could not last. As the ball began to roll down the energy landscape, the inflaton field started to decay towards its true, lower energy state. But the process of its decay released an unimaginable torrent of vacuum energy. This energy did not tear the universe apart. Instead, it performed a miracle. It drove a period of exponential expansion known as cosmic inflation. In a time span so brief it is almost meaningless to us, a fraction of a second, the universe doubled in size and then doubled again and again, over and over. A subatomic speck of space was stretched to a size larger than our entire observable universe today. This violent, hyper-fast smoothing ironed out any wrinkles, creating the remarkably flat and uniform cosmos we observe. But it did more than just smooth. As the inflaton field finally relaxed, it released its stored energy, reheating the universe and filling it with the hot plasma of particles that would eventually form atoms, stars, and galaxies. The seeds for all of this structure were quantum fluctuations in the inflaton field itself. Those tiny, random ripples in the vacuum, born from the same quantum uncertainty that creates virtual particles, were stretched to cosmic proportions by inflation. They became the faint overdensities, the gravitational seeds that, over billions of years, pulled matter together into the vast cosmic web of galaxies we see today. So the entire universe, in all its grandeur, may be nothing more than a quantum fluctuation on a cosmic scale, magnified and frozen in place by the creative power of a vacuum energy field. The same nothingness that could one day erase everything was the very engine that birthed it all. This theoretical energy of the void is not a vague concept. We can actually assign it a number, a density for the emptiness of space itself. According to our best theories of the quantum world, every single field that exists, from the electromagnetic field to the electron field, is constantly buzzing. And every possible way these fields can vibrate, every frequency and mode of that eternal hum, contributes a tiny bit of energy to the vacuum. When you add it all up, the sum of every possible fluctuation across all of existence, the number you get is beyond astronomical. It is, in fact, the largest number that has any meaning in theoretical physics. This calculation suggests that every single cubic centimeter of what we call empty space should contain more energy than the total mass energy of all the stars and galaxies in the entire visible universe. The vacuum should be a raging inferno of power, so dense that its gravitational effect would have curled the cosmos into a microscopic, not instantly after the Big Bang. Life, planets, and galaxies would have been impossible. Yet when we look out at the cosmos, we see something entirely different. Through the accelerating expansion of the universe, we can measure the actual energy density of empty space. The value we get is incredibly small, but it is positive. It is a faint, gentle pressure pushing the galaxies apart. But when you place the observed value next to the theoretical prediction, you are not looking at a small rounding error. The number from theory is larger than the number from observation by a factor of 1 with 120 zeros after it. To call this a discrepancy is the greatest understatement in all of science. It is a catastrophic failure of our understanding. This gaping void in our knowledge is not just a puzzle about nothingness. It is a screaming signal that we are fundamentally wrong about how the universe works at its deepest level. The two pillars of modern physics, quantum mechanics and general relativity, are completely at odds here. Quantum field theory calculates the energy, and general relativity dictates how that energy bends spacetime. But when we plug the quantum answer into Einstein's equations, the result is a universe that cannot exist. This tells us that we do not yet know how gravity talks to the quantum world. The vacuum energy catastrophe is therefore a silent guide, pointing directly to the chasm where our two greatest theories meet and shatter, waiting for a new idea to bridge the impossible divide. This fundamental conflict between our two greatest theories of physics is the heart of the problem. On one hand, we have general relativity, Einstein's magnificent description of gravity as the curvature of space and time itself. It tells us how mass and energy shape the cosmos, from the orbit of a planet to the expansion of the entire universe. On the other hand, we have quantum mechanics, the astonishingly accurate rules governing the subatomic world of particles and forces. Both theories are spectacularly successful in their own domains, but they speak completely different languages. When they try to talk about the same thing, like the energy of the vacuum, the conversation breaks down into nonsense. General relativity treats the vacuum energy as a single number, the cosmological constant, a fixed parameter you simply plug into the equations. It cannot tell us why that number has the tiny, specific value we observe. It just accepts it as a given fact about the universe. Quantum field theory, however, does try to calculate that number from first principles, by adding up the frantic energy of all the quantum fluctuations. But its answer is catastrophically wrong, producing a value so immense it would have destroyed the cosmos. So we are left with a maddening impasse. One theory gives a number that is impossibly huge, and the other theory just shrugs and uses the tiny number we see, with no explanation for why it is so small. This is not a minor technical issue. It is a screaming signal that we are missing a deeper layer of reality, a framework where gravity is not a classical force bending a smooth stage, but a quantum player in its own right, dancing alongside the other particles. This is the dream of quantum gravity, a single theory that would weave these two conflicting descriptions into one seamless fabric. Candidates like string theory or loop quantum gravity offer different paths. String theory proposes that the fundamental entities are not point-like particles but tiny, vibrating strings, and their different vibrations give rise to all the forces and particles, including the graviton, the hypothetical quantum of gravity. Loop quantum gravity suggests that space-time itself is not continuous, but is woven from a network of discrete, finite loops. In both cases, the aim is to describe the fabric of reality at the tiniest possible scale, the Planck length, where the quantum foam is not just a metaphor but the literal structure of space and time. It is here, at this ultimate frontier, that the true nature of the vacuum energy might finally be revealed. Perhaps in this theory, the contributions from the countless quantum fields cancel out in a beautifully symmetric way we have not yet grasped. Or maybe the vacuum energy is not a constant at all, but a dynamic quantity that has evolved over the life of the universe. The resolution of the cosmological constant problem likely lies hidden in the physics of quantum gravity, waiting to show us that the silent, simmering nothingness is far more structured and profound than we ever dreamed. So how do physicists even begin to handle a calculation that suggests an infinite energy for the void? They use a mathematical sleight of hand, a necessary and brilliant trick known as renormalization. The problem is straightforward, yet devastating. When you try to add up the contributions from every single possible quantum fluctuation, from the lowest energy waves to the highest energy vibrations, the sum does not just become large. It literally becomes infinite. An infinite energy density for empty space is a physical impossibility, a clear sign that our equations are breaking down when pushed to their absolute limits. Renormalization is the tool that rescues physics from this abyss. Think of it like this. You are trying to weigh a single, tiny feather, but you are forced to do it on a scale sitting on a wildly shaking platform. The vibrations are so intense that the needle swings to infinity, giving you a meaningless reading. Renormalization is the process of carefully measuring and then subtracting out the effect of that shaking platform, so you can finally see the true weight of the feather. In quantum field theory, this means identifying the infinite, unphysical parts of the calculation that come from our imperfect theories and cleanly subtracting them away. What remains are the finite, measurable quantities that we can actually test against experiments, like the mass of an electron or the strength of a force. It is a process that has been spectacularly successful, leading to predictions confirmed with breathtaking precision. But for the vacuum energy itself, for the cosmological constant, this brilliant trick fails completely. When we apply renormalization to this specific problem, we can subtract the infinity, but we are left with a result that is still astronomically huge, not the infinitesimally small number we observe. The mathematical tool that tamed every other infinity in particle physics is powerless here. This is not a failure of the technique, but a profound clue. It tells us that the cosmological constant problem is different in kind. It is a crisis that our current toolbox cannot fix, a silent scream from the vacuum that we are missing a fundamental truth about how the universe truly works on its deepest level. Faced with a calculation so catastrophically wrong, some physicists have turned to a startlingly different kind of explanation, one that shifts the entire focus of the question. This is the Anthropic Principle, a deeply controversial idea that suggests the answer might not lie in a fundamental law of physics, but in the simple fact of our own existence. The reasoning is as elegant as it is unsettling. If the vacuum energy, the cosmological constant, were even slightly larger than the tiny value we measure, the consequences would have been immediate and absolute. A stronger repulsive force from empty space would have driven the universe to expand at a ferocious rate from the very beginning. Matter would never have had a chance to clump together under gravity. No galaxies would have condensed from the primordial gas. No stars would ever have ignited. No planets would have formed. In such a frantic, empty cosmos, the complex chemistry required for life would have been impossible. We, quite simply, would not be here to ponder the silence. So why does our universe have this peculiarly small, life-permitting value for the vacuum energy? The anthropic answer is that it could not have been any other way. We do not observe a universe with a lethal amount of vacuum energy because such a universe would be sterile and empty, with no observers to witness its existence. This reframes the entire mystery. We stop asking why the laws of physics produce this specific number, and instead ask a different question: in which kinds of universes can conscious life emerge? This line of thinking finds a natural, if speculative, home within the concept of the multiverse. Imagine a vast and eternal cosmic landscape where countless universes are constantly bubbling into existence, each with its own random set of physical constants. In most of these universes, the dice roll badly. The vacuum energy is far too high, and those universes remain forever dark and lifeless. In an incredibly rare subset, by pure chance, the numbers come out just right. The cosmological constant is small. Gravity can work its slow magic, and stars and planets and eventually observers can arise. We, of course, find ourselves in one of those exceptionally rare, life-friendly bubbles, not because it is special, but because it is the only kind of bubble we could possibly inhabit. For many scientists, this is a profoundly unsatisfying answer, a retreat from the hope of a unique, elegant theory that predicts our world. It feels like giving up, explaining one mystery by invoking an even bigger one, an infinite ensemble of unseen worlds. Yet for others, it is a necessary and humbling acknowledgement that our universe might not be tailor-made for us, but rather, we are the accidental guests in a single, habitable room within an infinite, and mostly uninhabitable, cosmic hotel. To find a path out of this impasse, we must venture into one of the most ambitious and controversial ideas in modern physics, the string theory landscape. String theory itself proposes that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The different vibrational patterns of these strings give rise to all the forces and particles we observe. But a profound consequence of this theory is that it may not predict a single, unique universe. Instead, the mathematics suggests a staggering number of possible stable configurations for the vacuum itself. The number of these possible vacuum states is beyond human comprehension, perhaps as many as 1 followed by 500 zeros. Each of these vacua represents a universe with its own unique set of physical laws, its own values for the constants of nature, and crucially, its own specific amount of vacuum energy. In this breathtaking cosmic landscape, our universe is not the whole story. It is merely one bubble in a frothing, infinite multiverse, a single possibility that randomly actualized with a cosmological constant small enough to allow for galaxies, stars, and life. This framework completely reframes the cosmological constant problem. We are no longer asking why the laws of physics inevitably lead to our specific, tiny value. The question shifts. We are now asking why we, as observers, find ourselves in a universe that permits our existence. The answer becomes a matter of sheer statistics and selection. In the overwhelming vastness of the multiverse, almost every bubble universe has a vacuum energy value that is lethal. Those universes expand too fast or collapse too quickly, forever remaining dark and empty. But in an infinitesimally small fraction of these bubbles, by pure random chance, the numbers line up just right. In those rare, habitable pockets, the vacuum energy is weak enough for gravity to pull matter together, and for the long, slow dance of cosmic evolution to begin. We could not possibly find ourselves anywhere else. This perspective is as humbling as it is radical. It suggests that the deepest laws of our reality might not be fundamental, necessary truths, but merely local bylaws, the accidental outcome of a cosmic lottery draw that we happen to win. The search for a single, elegant equation that explains our universe's peculiar fine-tuning might be a fool's errand if our cosmos is just one among a near infinity of others, most of them stillborn and barren. This quiet apocalypse hinges on a single, random quantum event known as bubble nucleation. To grasp its mechanics, picture a bottle of pure water that has been supercooled far below its normal freezing point. The water remains a liquid, but it is in a fragile, metastable state. It yearns to become ice. All it needs is a trigger, a single seed crystal, a tiny impurity, or even just a sharp jolt. The moment that nucleation point appears, the change is instantaneous and total. The liquid water does not freeze gradually from the edges inward. Instead, a front of crystallization erupts from that single point and races outward at a tremendous speed, transforming the entire volume into solid ice in a flash. Our vacuum may exist in a similar state of precarious stability. Our universe feels solid and permanent, with its stable atoms and fixed laws of physics. But this might be an illusion of our limited perspective in both space and time. We could be living in a cosmic supercooled liquid, a false vacuum. The ball is not resting at the absolute bottom of the valley. It is perched on a small ledge, a local minimum that feels secure but is separated by a mere energy hill from a far deeper, more stable chasm. The true vacuum. The process that could kick us off that ledge is quantum tunneling. In the everyday world, a ball cannot spontaneously pass through a solid wall. But in the quantum realm, particles and fields can perform this impossible feat. There is a small, but non-zero, probability that they can simply disappear from one side of an energy barrier and reappear on the other, as if the barrier was not even there. In the infinite expanse of our universe, within the endless churn of the quantum foam, it is statistically possible for a random fluctuation, a high-energy pop, to provide just enough energy for the Higgs field to tunnel through its barrier. At that precise location in space and time, a microscopic bubble of true vacuum would be born. The probability of this happening in any given cubic centimeter of space in any given second is astronomically small, so low that it is effectively zero for all human concerns. But the universe is vast and ancient. It contains an unimaginable number of cubic centimeters and has existed for nearly 14 billion years. When you multiply an infinitesimally small probability by an almost infinitely large number of opportunities, the result is no longer zero. It becomes a cosmic certainty over a long enough timeline. This is why physicists cannot dismiss the threat, even as they assure us it is not imminent. The clock is ticking on a scale so grand we can barely comprehend it. A timer set for an event that may not occur for countless trillions of years, or one that could be triggered before you finish this sentence. The silence of the void is being challenged in the most violent experiments humanity has ever devised. We are not waiting for a cosmic bubble to find us. Instead, we are actively probing the fabric of reality, searching for the cracks in our vacuum's foundation. The front line in this search is not a telescope, but a machine buried deep underground, the Large Hadron Collider. By smashing protons together at velocities infinitesimally close to the speed of light, we recreate, for a fleeting instant, the conditions of the primordial universe. Within the debris of these collisions, we hunt for the Higgs boson, the particle that is a tangible manifestation of the Higgs field. Its properties are the key to our cosmic fate. By measuring the mass of the Higgs boson with exquisite precision, and by studying how it interacts with other fundamental particles, especially the top quark, physicists can perform a profound calculation. They can map the shape of the Higgs field's energy landscape. They can determine whether the valley we reside in is truly the deepest one, or if it is merely a shallow depression on the slope of a much deeper abyss. The current data paints a fascinating and nerve-wracking picture. It suggests that our universe is in a state of metastability. Our vacuum is not perfectly stable, nor is it imminently dangerous. It is that ball resting on a ledge, seemingly secure for now. The calculation indicates that the energy barrier separating us from the true vacuum is incredibly high, meaning the probability of a quantum tunnel event is extraordinarily low. But it is not zero. This is not a cause for panic, but a call for more profound investigation. The uncertainty in our measurements means we cannot yet be sure of the exact shape of the cliff we are standing on. Is the ledge wide and sturdy, or is it narrow and crumbling? Determining this with absolute certainty is one of the primary scientific goals for the next generation of particle colliders. Every new collision, every new measurement of the Higgs, is like taking a core sample from the bedrock of reality itself, helping us understand whether our universe is built to last or is merely temporary. This same restless vacuum energy holds the key to the ultimate fate of the universe's most enigmatic objects. The edge of a black hole is a place where the fabric of reality is stretched to its absolute limit. And here, the quantum vacuum behaves in a way that defies classical intuition. According to the framework of quantum field theory in curved spacetime, the immense gravitational pull warps the very stage upon which the vacuum's endless dance occurs. It distorts the quantum fluctuations near the event horizon, the point of no return. Normally, a virtual particle pair will appear and annihilate in perfect balance. But when this dance happens at the precipice of a black hole, the gravitational tidal forces can tear the pair apart. One particle falls across the event horizon, forever lost to the black hole's interior, while its partner is ejected outward, escaping into the universe as real radiation. This is the mechanism of Hawking radiation. From our perspective, it appears as if the black hole itself is glowing, emitting a faint thermal glow of particles. The energy for this process comes directly from the black hole's own mass. The infalling particle has negative energy relative to the outside universe, and when it falls in, It reduces the total mass and energy of the black hole. Over time, this slow, steady trickle of radiation acts like a persistent evaporation. A stellar mass black hole would take trillions upon trillions of years to evaporate significantly, but the process is inexorable. For the smallest theoretical black holes, the evaporation would eventually accelerate into a final, explosive flash of energy. In this profound transformation, the vacuum energy is not creating or destroying in a grand cataclysm. It is performing a slow, alchemical conversion, turning the ultimate manifestation of gravity, a black hole, back into pure radiation. This establishes a deep and unexpected bridge between the three great pillars of physics. Quantum mechanics provides the virtual particles, general relativity provides the warped spacetime that separates them, and thermodynamics provides the laws governing the black hole's temperature and entropy. The silent activity of the void is not just a background hum. It is an active participant in the cosmic cycle of birth and decay, slowly unraveling the universe's most perfect traps. But the strange influence of motion on reality does not end at the event horizon. The vacuum itself shifts its nature based on how you move through it. Picture two astronauts floating in the deep void, far from any star. One of them, Alice, continues to drift peacefully. She feels nothing, sees nothing, and measures her surroundings as a perfect, cold, empty vacuum. The other astronaut, Bob, suddenly fires his rocket pack, accelerating at a tremendous and constant rate. As he speeds up, something remarkable happens to his perception of the same empty space that Alice finds barren. His instruments begin to detect a faint warmth. He finds himself surrounded by a uniform bath of real particles, a gentle heat radiation filling his entire universe. This is the Unruh Effect, a stunning prediction of quantum field theory. The vacuum itself has become a warm thermal bath, but only for Bob. Alice, floating inertially, still reports a perfect and silent void. Both are correct. There is no single objective answer to the question of what is truly in the empty space between them. The concept of a particle, one of the most fundamental building blocks of reality, is not an absolute truth. It is a relative one, defined by the observer's own state of motion. An accelerating observer like Bob is constantly crossing through different slices of space-time, and this motion mixes the positive and negative frequency modes of the quantum fields in such a way that what was a vacuum state for Alice becomes a thermal state for him. The energy of the void is not a fixed number written on the fabric of the cosmos. It is, in a very real sense, in the eye of the beholder. This reveals a profound relational nature at the heart of physics. The vacuum state, the very definition of nothingness, is not an invariant background. It is a dynamic stage that changes its appearance depending on who is looking and how they are moving. This forces us to abandon the classical idea of a single, true reality that all observers would agree upon. At the quantum level, your experience of existence, even your perception of nothing at all, is intimately tied to your own journey through the cosmos. This restless nothingness forces us to confront a question that has haunted philosophers for millennia. Why is there something rather than nothing? For centuries, the concept of nothing was absolute, a pure and sterile void, the ultimate non-being from which existence was a stark and inexplicable departure. But the quantum vacuum shatters this classical view. It reveals that what we called nothing is not an absence at all, but a vibrant, energetic plenum, a foundational ground humming with potential. The line between something and nothing becomes impossibly blurred. Those virtual particles that wink in and out of existence, are they something or are they nothing? They are a ghostly middle ground, a perpetual flicker at the boundary of being. This suggests a cosmos where existence is not an anomaly to be explained, but an inevitable flowering from a deeper, more fundamental state of activity. The universe may not have come from a sterile, philosophical nothing. It may have emerged from this dynamic void. a something so rich and fecund that the appearance of stars and planets was almost guaranteed. This places modern physics squarely at the center of the oldest metaphysical inquiry. We are no longer just asking what the universe is made of, but probing the very nature of being itself. Is the stable, tangible world we experience merely a temporary pattern, a kind of froth on the surface of this seething quantum ocean? If the vacuum is this active, this creative, then our entire reality might be a subtle and complex excitation of an underlying field of pure potential. The mystery of our existence shifts from a question of cosmic genesis to a question of cosmic structure. We are not here despite the void, but because of its hidden, vibrant nature. The answer to why there is something may be that true nothingness, in the absolute philosophical sense, was never even a possibility. This relentless forward march of time from past to future feels like the most fundamental rule of our existence. Yet physics cannot fully explain why we remember yesterday but not tomorrow. The answer to this mystery, the arrow of time, might be hidden within the same vacuum energy that birthed the cosmos. Our experience of time's flow is intimately tied to the concept of entropy, the measure of disorder in a system. The universe always moves from order to disorder, from a state of low entropy to high entropy, and it is this irreversible increase that gives time its direction. Think of a drop of ink falling into a glass of clear water. It starts in a highly ordered, low-entropy state, a single concentrated drop. It will never spontaneously gather itself back into that drop. It will only spread out, mixing into a uniform, high-entropy solution. The entire universe is doing the same thing on a cosmic scale, but it began with a puzzle. Why was the early universe in such an incredibly ordered, low-entropy state to begin with? The smooth, uniform distribution of matter and energy after the Big Bang was a state of astonishingly low disorder, a wound-up spring that has been uncoiling ever since, driving the arrow of time forward. The key to this initial condition may lie in the vacuum energy of the inflatoned field. During the period of cosmic inflation, the universe was trapped in a false vacuum state of incredibly high energy. This state is thought to have been perfectly uniform, a state of maximum order and minimum entropy. It was the ultimate wound-up spring. As the inflatoned field decayed and released its vacuum energy, it did not just create particles, it also set the stage for the creation of disorder. That release of energy was like tipping the first domino, initiating a chain reaction of cosmic complexity. The quantum fluctuations in the inflatoned field, stretched to cosmic size, became the seeds for all future structure, galaxies, stars, and planets. These structures represent pockets of localized order, but they are forged by dispersing immense amounts of energy and heat into the void, increasing the overall entropy of the cosmos. So the vacuum energy did not just create space and matter. It may have also created the initial conditions for time itself to have a direction. The low entropy beginning was forged in the fiery, ordered vacuum of inflation, and the entire subsequent history of the universe, including our own perception of past and future, is just the long, slow uncoiling of that single, primordial state. The vacuum, therefore, is not just the stage upon which time plays out. It could be the very reason the play only moves forward. But this quantum sea might be more than just a chaotic foam. It could possess the perfectly ordered structure of a superfluid. Imagine a fluid with absolutely no internal friction, a substance that flows forever without losing energy. This is the strange state of superfluidity, observed in ultra-cold liquids like helium when they are cooled to near absolute zero. In this state, the fluid loses all viscosity and can climb the walls of its container in a thin film, defying gravity. Now, take this concept and apply it to the fabric of the cosmos itself. Some of the most ambitious theories in physics propose that the vacuum of space is not just an active medium, but a cosmic superfluid. In this view, empty space is not truly empty. It is a condensate, a coherent ground state formed from more fundamental entities, perhaps the hypothetical gravitons that carry the force of gravity, or even tinier strings from string theory. This superfluid vacuum theory attempts to bridge the chasm between general relativity and quantum mechanics by reimagining the very stage of reality. What we perceive as the force of gravity might not be a curvature of a geometric spacetime, but rather an emergent effect, a kind of pressure or resistance generated by our motion through this superfluid medium. Think of a fish swimming through water. The water pushes back against the fish's fins, creating the forces that allow it to maneuver. In a similar way, an object moving through the superfluid vacuum could experience a pushback that we interpret as inertia. And the presence of a massive object like a star could create a kind of pressure gradient or vortex in the superfluid, which would guide other objects along curved paths, perfectly mimicking what we call gravity. This is not just a change of language. It is a profound shift in perspective, where the most fundamental forces are not primary, but secondary, emerging from the complex interactions within an underlying, fluid-like reality. While this idea remains highly speculative, it offers a breathtakingly elegant way to visualize the cosmos. The silent void between stars is transformed from a passive stage into a dynamic, flowing entity, a perfect fluid whose hidden currents might ultimately dictate the motion of every planet, star, and galaxy. The dream of limitless power has long danced at the edges of science fiction, promising a future fueled by the energy of the vacuum itself. It is a compelling vision, to build an engine that runs on nothingness. Yet the cold, hard laws of physics present a wall of impossibility that even our most brilliant engineers cannot scale. The quantum vacuum is not a reservoir waiting to be tapped. It is the absolute baseline, the lowest rung on the universal energy ladder. Trying to extract useful work from it is like trying to sip water from an empty cup. You cannot go lower than the ground state. Any machine we could possibly build, any circuit or device, would already be sitting on top of this energy floor. To pull energy out, you need a difference in potential, a place of higher energy and a place of lower energy for that energy to flow. But the vacuum is the lowest possible state. There is no downhill from here for energy to flow toward. The vacuum energy is not a hidden battery. It is the table upon which the cosmic meal is set, and you cannot power a city by eating the table. This fundamental misunderstanding often arises from a confusion with effects we can measure, like the Casimir force. We see those plates being pushed together by the vacuum's activity, and think we are witnessing a source of power. But that force is a result of a pressure difference, a boundary effect. To harness it for continuous energy, you would have to repeatedly pull the plates apart against the force, which requires you to put more energy into the system than you could ever get back out. It is a demonstration of the vacuum's reality, not a blueprint for a perpetual motion machine. The cosmos offers this immense power, but it is a power locked in a perfect, unbreakable equilibrium. The dream of vacuum energy engines crashes against the simple, profound truth that you cannot get something for nothing, not even from nothing itself. The silent hum of the void is the next great frontier for science. Our cosmic fate hinges on answering two profound questions. Is the vacuum we inhabit truly stable, or are we living on borrowed time? And why does the energy of empty space have the bafflingly small value that it does? The quest for these answers is driving a new generation of experiments that will push the boundaries of technology and thought. On Earth, the next era of particle colliders will probe the Higgs boson with even greater precision. By measuring its properties to an incredible degree of accuracy, we can finally map the exact shape of the energy landscape we reside in. We will know if our valley is the true bottom of the cosmic well or just a temporary resting place on the edge of a cliff. In space, Powerful new telescopes will scrutinize the expansion of the universe with unprecedented detail. By observing how the rate of expansion has changed over billions of years, we can decipher the true nature of dark energy, testing whether it is a constant vacuum energy or something even stranger. These observatories will also read the faint afterglow of the Big Bang, the cosmic microwave background, like a cosmic fingerprint, searching for imprints from the primordial vacuum that could reveal secrets of its origin. Yet all these experiments point toward a single, ultimate goal: the unification of gravity and quantum mechanics. The vacuum energy catastrophe is the loudest clue that our current theories are incomplete. The final answer will not come from a single observation, but from a new conceptual framework, a theory of quantum gravity that seamlessly weaves together the very large and the very small. Whether it is through string theory, loop quantum gravity, or an idea yet unimagined, this theory must naturally explain why the energy of nothing is not an infinite, universe-shattering force, but the faint, gentle pressure we observe. The resolution of this puzzle will do more than just solve a math problem. It will redefine our understanding of nothingness itself, revealing the hidden architecture of reality and our place within it. Even light itself is not immune to the ghostly influence of the void as it travels across the cosmos. The quantum vacuum subtly reshapes the path of every photon, a phenomenon known as vacuum polarization. Imagine a single electron floating in space, its negative charge creating an electric field that extends outward. In the classical world, that field is a simple, smooth gradient. But the quantum vacuum complicates this picture. At any moment, a virtual electron and its antiparticle, a positron, can pop into existence right near the real electron. In their fleeting lifetime, these virtual pairs act like tiny electric dipoles. The positively charged virtual positron is attracted to the real electron, while the negatively charged virtual electron is repelled. This momentary alignment of the virtual pairs creates a screen, a kind of polarization cloud that partially masks the true, bare charge of the original electron. From a distance, its charge appears slightly weaker than it fundamentally is. This screening effect means the vacuum itself acts as a subtle dielectric medium, slightly altering the electromagnetic force between charged particles. It is a correction so small it is usually negligible, but it is a real, measurable effect that confirms the vacuum is an active player in the most fundamental interactions. This influence becomes spectacularly visible under the most extreme conditions. In the presence of immensely powerful electromagnetic fields, like those surrounding a heavy atomic nucleus or in the aftermath of a gamma-ray burst, the vacuum can no longer be treated as a gentle screen. It becomes a nonlinear medium, a frothing sea where photons can no longer simply pass through one another like ghosts. Instead, they can interact, scattering off each other in a process called light-by-light scattering. Two beams of light, crossing in a perfect vacuum, can very rarely deflect one another. They do not touch directly, of course. They interact through the ghostly intermediary of the vacuum. One photon temporarily fluctuates into a virtual electron-positron pair, which then interacts with the second photon before vanishing back into the void. It is a ghostly dance where light interacts with light, mediated by the restless nothingness between them. This incredible prediction of quantum electrodynamics was confirmed at the Large Hadron Collider, proving once and for all that the vacuum is not an empty stage. It is a dynamic, responsive entity that bends, screens, and even facilitates the most ethereal of interactions, shaping the very light by which we see the universe. This strange balance in our cosmic era feels almost too perfect to be an accident. For nearly the entire history of the universe, matter was the undisputed ruler of the cosmos. Its gravitational pull dominated, slowing the expansion from the Big Bang, pulling gas together to form the first galaxies, and sculpting the vast cosmic web. Dark energy, the potential energy of the vacuum, was there all along, but its effect was utterly negligible, a whisper drowned out by the roaring pull of gravity. Then, as the universe expanded and matter diluted, spreading ever more thinly across the void, its gravitational grip began to weaken. Around 5 billion years ago, something remarkable happened. The density of matter fell to a point where it became roughly equal to the constant, unchanging energy density of the vacuum. And in that moment, the balance of cosmic power shifted. The universe transitioned from decelerating under gravity's pull to accelerating under the vacuum's gentle, relentless push. We now live in this incredibly narrow window of time, a brief slice of cosmic history where these two fundamental densities are comparable. This is the cosmic coincidence, and it poses a profound puzzle. Why do we, as conscious observers, find ourselves in the universe at the precise moment when matter and dark energy are in such a delicate balance? For the vast majority of the past, this was not true. And for the infinite future that lies ahead, it will not be true either. Dark energy's influence is constant, while matter will only continue to thin out. Billions of years from now, the vacuum energy will be millions of times more dominant than matter, driving an exponential expansion that will tear the cosmic web apart and isolate all galaxies in a cold, dark, and empty cosmos. The fact that we exist in this fleeting transitional period, this special moment of near equality, seems far too convenient. Is this just a lucky break, a random bit of timing in our cosmic calendar? Or does our very presence as observers somehow explain the timing? This adds a deeply philosophical layer to the vacuum energy mystery. It is not just a question of what dark energy is, but why it reveals its influence at the exact epoch when intelligent life emerges to notice it. The silence of the void is not just a physical force, but a chronological riddle waiting for its solution. From the seething quantum foam to the accelerating edge of the cosmos, we have traced the invisible threads of vacuum energy. This profound nothingness is the hidden architect of our reality, a force that sculpted the universe in a fiery burst of inflation and now silently pushes the galaxies apart. It is both creator and potential destroyer, a cosmic paradox resting at the very heart of physics. This journey reveals a cosmos where emptiness is alive with potential, where the fate of everything is written into the silent hum of the void. The greatest mysteries of existence are not always found in the distant stars, but in the profound nature of the space between them. We stand at the frontier of this understanding, where the clash between quantum mechanics and gravity points toward a deeper truth waiting to be uncovered. The universe is far stranger and more wondrous than we ever dreamed. Let this exploration be your starting point. What does this cosmic paradox make you wonder about our place in the vastness of space? Share your thoughts below, and subscribe to continue unraveling the universe's greatest secrets.